Yeah, I'm here with Ali to sort of give you a pitch for this new course that we're developing and we'll be teaching in the winter quarter. And it's, as you see, Engineering Energy Policy, Policy Change. Currently listed as MatSci 301. We're going to seek cross-listing with a number of other departments and schools across the university. This is brought to us through the assistance of the Precourt Institute for Energy. So I want to begin by thanking them for their support for this, helping us with this course. And just to give a little bit of a background, the Precourt Institute is an organization that sort of spans everything from policy to really hardcore energy science here at Stanford. It involves faculty members and students from all across the university. They organize a really great seminar series, the Energy Seminar. Ali was a former energy seminar speaker. So we bring energy experts to campus throughout the academic year on Mondays. That was, I think, kind of the kickoff academic offering of the Institute. And this course is an additional offering that we have focusing more on the intersection of research and energy policy in the United States. Ali, did you want to add?
Sure. One of the ways that we're going to approach this is really by honing in on a couple of processes that people use in Washington to formulate policy that relates to science, engineering, and technology. And, you know, we felt like one of the ways that was captivating to do that was to really hone in on this concept of moonshots and how that gets constructed, how you really think about that, all the way from communicating the idea to other people to working on the technical details to the budget and the implementation around that. I spent 8 years in the Obama administration, and so was very proximate to this sort of churn of how do you take technology ideas and get people fired up about spending research dollars and moving the country and the world forward along cost curves and really unlocking the impact. So just to, I think as a sort of a preview version of what the class is like, well, not really, but we wanted to sort of show you what we're talking about.
For the eyes of the world now look into space, to the moon, and to the planets beyond. And we have vowed that we shall not see it governed by a hostile flag of conquest, but by a banner of freedom and peace. We have vowed that we shall not see space filled with weapons of mass destruction, but with instruments of knowledge and understanding. Yet the vows of this nation can only be fulfilled if we in this nation are first, and therefore we intend to be first. In short, our leadership in science and industry, our hopes for peace and security, our obligations to ourselves as well as others, all require us to make this effort, to solve these mysteries, to solve them for the good of all men, and to become the world's leading spacefaring nation. We set sail on this new sea because there is new knowledge to be gained and new rights to be won, and they must be won and used for the progress of all people. For space science, like nuclear science and all technology, has no conscience of its own. Whether it will become a force for good or ill depends on man. And only if the United States occupies a position of preeminence can we help decide whether this new ocean will be a sea of peace or a new terrifying theater of war. I do not say that we should or will go, unprotected against the hostile misuse of space any more than we go unprotected against the hostile use of land or sea. But I do say that space can be explored and mastered without feeding the fires of war, without repeating the mistakes that man has made in extending his writ around this globe of ours. There is no strife, no prejudice, no national conflict in outer space as yet. Its hazards are hostile to us all. Its conquest deserves the best of all mankind, and its opportunity for peaceful cooperation may never come again. But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Big change in political discourse since then.
So Paul will walk us through a little bit how that actually panned out and whether what the president at the time promised materialized. But I want to provide a little bit of context. First, it's really fitting because this speech happened this week a bunch of years ago. And
55 years ago.
55 bunch of years ago. And what if you listen to the whole 18 minutes, I think it lays out the thesis of this course, both in what it did and what it didn't do. So President Kennedy at the end talks about the budget. He talks about implementation, whether it's going to be challenging or not. He hadn't really talked to the scientists when he developed the budget and the implementation. That sort of came on the back end. And so part of what we'll talk about is when you're constructing an idea like that, how much detail do you need to have? And if you don't focus on some of the detail, like the budget and implementation, what goes wrong? I think the second piece we really want to focus on is we will, for the same motivations he laid out in that speech, be trying to solve those same sort of aspirational challenges in energy and in climate. And part of the role is for folks in Washington who are policymakers every day to reach out and take advantage of the human capital that exists outside of Washington. But part of it's on the human capital outside of Washington to reach in and say, hey, don't screw this up because we're all counting on it turning out the right way. And so this course is really focused on making sure you're equipped to do that second piece. And if someone calls you from Washington, to be able to know how to take the most advantage of that in steering the direction of the policy in the right way.
Okay, very good. So just getting back to the original Moonshot, the Apollo program that was announced in this speech by John F. Kennedy. It was, in many ways, a huge boon to this country and to the world through the technological spin-offs that resulted from it. A lot of the efforts in miniaturization of computers and semiconductors, communications equipment, medical diagnostics, that goes on and on, all of the different spin-offs that came from this program, which was really part of the competition that existed between the United States and the Soviet Union. And there was a major geopolitical aspect to this whole program, beyond all of the important science and learning that he talks about in the speech. That there was clearly this competition that was critical. In terms of the budget, it went way over budget, and it wouldn't have been able to do that if there hadn't been this geopolitical competition, because Congress was basically going to continue to write checks. If they could beat the Soviet Union to the moon, that was good enough for them. And so they wrote huge checks.
You don't always get that lucky.
Yeah, and so that So there was, I think, it was a success. It took less than the time that was specified. He said by the end of this decade. It happened maybe 4 or 5 months before the end of the decade. A lot of the people involved in space exploration at that time were shocked with this timeline that was announced, and there was some doubt that it could be done, but they did it. But they also had effectively unlimited resources of the wealthiest nation on the planet to make it happen.
So why do we use the moonshot as an entry point into the policy discussion? In my time in the administration, I actually worked a year for Steve Chu, who teaches here, and he got his Nobel Prize for essentially slowing down atoms in what he calls optical molasses, or what maybe the field calls optical molasses now. And in Washington, physicists get Nobel Prizes, and really no one understands why or what the sort of purpose is. And so, the Steve Chus of the world are really good at turning that into an analogy and helping people understand. And I'll use that as an analogy to sort of explain this course. In policy, there's a lot of stuff that's moving around really fast. And to be able to really understand what each piece of the policy sort of ecosystem does, you have to slow it down. And there are very few moments in time when the policy process actually slows down. The generation of aspirational goals like a moonshot is one of those moments. You actually get to suspend the whole dynamic for a second, look at all of the pieces, and articulate a new direction. So think of the moonshot as sort of our optical molasses for the ecosystem of policymaking, and it's a tool for us to help you sort of get a sense of how all of the pieces fit together. We'll do that in part by looking at case studies of things that either have gone well or have gone incredibly poorly in the energy domain. So we will look at case studies of research in the energy domain. The second thing we'll do is really engage practitioners in the field. You will get some practice doing things maybe you'll never do again, but it will help you understand that those things are there and someone is struggling through it. I sort of took comfort in that, working side by side the president's science advisor, knowing there was someone there to do that piece, and he took comfort knowing that I was doing some of the other stuff. I think for a lot of you, just getting that awareness that someone else is doing some of this work will be helpful. And part of the way we'll do that is by bringing in practitioners beyond just people who are practicing sort of science and engineering, but other sort of disciplines in this domain. We'll try to get you to take a crack at writing plug into a speech like that and workshop it with you, and workshop it with real speech writers to see how you fare and whether you can come up with a laugh line in a science speech.
Okay, so we've shown the moonshot speech by Kennedy. Of course, there were even before that there were examples of huge efforts to sort of change the world with science and with a government-led process. And the Manhattan Project in World War II is a famous example of this. That was another program that had effectively unlimited resources and was attempting to win the war before the nation's enemies could develop these weapons. And as a result of the Manhattan Project and other big science projects during World War II, there was a realization in Washington that there was value for federal funding of scientific research at a high level, much of it occurring at universities. And there was especially value in what we call big science projects. So big facilities would bring together lots of people from different disciplines, like just as what happened in Los Alamos, New Mexico. But this would occur in large part at universities around the country. And so big facilities were built, and we have one of them here at Stanford. It was built a little bit after the war in the early 1960s, SLAC. And it started out as a particle accelerator. And there was a big emphasis in federal funding for physics and particle physics in particular, because it was going to get at the mysteries of how elementary particles worked and how this was important potentially for things like building future weapons, but in just understanding the world physically. So they built these enormous instruments, and SLAC is started out as a linear particle accelerator. And of course it evolved over time. So it turned out there were other things that you can do other than just accelerate particles to very close to the speed of light and bash them into each other and see what happens. You can actually, as was shown and worked on here starting in the early 1970s, you can actually shoot this beam of electrons into what's called a storage ring. And as it passes through that storage ring through magnetic fields, it emits radiation, light, called synchrotron radiation. And that light is very bright, and it can be tuned to very precise energies. So it can be used for a wide variety of experiments that are really not possible otherwise. And when I came to Stanford about 20 years ago, for me this was fabulous because I wanted to study materials for nanoelectronics. So I wanted to look at really, really small little bits of material and try to understand their structure and how they were put together. And we could use the synchrotron light to look at the way it was, the chemical bonding worked in these materials and what the composition was, even though they were very defective and small and disordered. Other things that you can do with the same kind of principle, basically passing electrons through magnetic fields in a clever way, you can create what's called a free electron laser. This was invented here at Stanford in the 1970s by Tom Mady. And it is now a world-class, sort of almost unique in the world, I guess, still, instrument, the linear coherent light source. It's the brightest light source in the world and can be used for time-resolved experiments, looking at things that occur at a very, very small time scale. So there's new science that these things continue to produce for us, and those of us who work here at Stanford have great opportunity to use these instruments. But it came about as a result of this Manhattan Project experience, a moonshot even before the moonshot.
And I'll just underscore that the solar program over the last several years of the Department of Energy has been as an example of that. And I think to underscore one of Paul's points, there are people really far afield from solar who got impacted by that. So you were a material scientist or you worked on power electronics and maybe didn't think about solar at all. A program like that can sort of suck you in. But just to sort of round this out relatively quickly here, Moonshots are a really great entry point. They're obviously not the whole policy dialogue, and so we will spend some time doing sort of complementary toolkit filling, talk to you about how policy gets made in gunshot scenarios. That's the sort of crisis that happens after a Deepwater Horizon spill or Fukushima or Flint. And people with STEM backgrounds are incredibly valuable in those moments. As well as the sort of regular order of day-to-day churn. For a lot of you, that might be ultimately end up being the only way you really touch the system over the course of your career. And we've talked a little bit about this already, so I don't want to dwell on it and would rather get to, if anyone has questions, focus on case studies. Anyone who takes the class will pick a moonshot themselves. It will have to be in one of these two categories, which are really, really broad, so you can pretty much pick anything. And you will develop the scientific and technical basis for a moonshot. You'll develop the budget for it. You'll really start to think about the communications for it. And I think that will help you, even if you never go to Washington, it will help you understand what they're doing, because you'll only interact with the communication side of it sometimes through the paper, and influence the direction of that. So, bottom line, the class it's more for Paul than for me. but I think part of the purpose of us pairing up together is for you to recognize there are people like me who are going to spend a big chunk of their professional careers in policy-making roles, and there are people like Paul who are going to spend a big chunk of their careers in academia. And both of us have to be aware of what the other person is doing for the science to move forward as quickly as it needs to. So these are sort of the nuts and bolts, and I think we have a couple minutes, so let's take questions.
each of your backgrounds, and how did it bring you to here today?
Sure. So I started working on economic policy broadly. Got into the Obama administration through the campaign, worked on the sort of global recession and our response to that. A big response to that was to build the economy that was going to dominate the future, which was the clean energy economy. And that got me sucked into working on these issues, and in the process realizing how much risk climate posed to the economy we were building. And so I've gotten sort of hooked on the climate clean energy bandwagon, and am just sort of a huge believer in the power of technology to open up the policy aperture, whether it's the policy aperture domestically or in any other country.
Okay. Well, I'm an engineer, and I got interested in materials when I was an undergraduate, and got really fired up as a graduate student about a long time ago now, 30-something years ago, to look at superconducting materials. There were new materials, new high-temperature superconductors that were discovered at that time. And that kind of led me into an interest in materials that are important in electronics, communication, and energy. There's big applications of these things in energy as well. I came to Stanford a little over 20 years ago, and I had been in industry for a few years before that, doing industrial research. And I love being here, and of course my time here has coincided with a major kind of restructuring of the world's energy economy, and in response to that, the rise of renewable energy and a lot of really interesting and difficult research questions associated with how do you make effective use of renewable energy, and how do you store it, because it tends to be intermittent. And a lot of these, it turns out, are materials-related problems. There's lots of other science and engineering that's part of this, so I have a view onto part of that. But energy is a really important part of what I do and what we do. And I've always been intrigued by this connection between sort of the sausage making of policy in Washington and what we actually see here as practicing researchers and academics. And I want to learn this stuff. So I thought it'd be fun to be part of it.
And I want to learn from you guys. So it's...
Yeah.
Oh, thank you. So the examples of programs that you guys mentioned that got significant funding, as you said, all had substantial benefits that weren't necessarily a part of the initial vision of the program. So I guess my question for you is, how do you conquer that? Something, especially in an environment like Washington, where people seem like they're asking questions more along the lines of, what can this do for us now?
Yeah, I mean, look, part of it is you're not going to account for it when you're trying to get people sold on the idea. So you have to overwhelm them with the sort of possibility that you're unlocking. And then part of it is, you have to build your principal case around what you're trying to accomplish, and then you buttress it with data points that show accidentally we discovered all of these other things when we did X. So it's a sort of a complex challenge, and I think one of the things that people in Washington struggle with a lot is how do you get people fired up about basic research, period, that's not tied to a moonshot, and that's a struggle because there's a sense of, well, I want to unlock some new economic potential. Why do I need this? And there I think you rely a lot on past data. But the reality is that data is not as sharp, and the cause and effect is hard to trace. And so you need things like moonshots to really pull the whole system along. Otherwise, I think your system starts to atrophy.
So a big part of actually getting policy through seems to be compromise in today's world. Do you guys focus on how to compromise or kind of sacrifice one part of policy making to get something else out of it throughout the course?
So one of the things we're going to do is, at the end of the course, people will have to defend their proposal to an expert panel, and part of the stress test will be, can we afford to do this? What is the trade-off? Who's succeeding? Who's the loser in this case? And that's what is the sort of analytical predicate to the compromise, right? You have to ask those questions. So we will walk you across those coals, and then you will know what the puts and takes are, and I think prepare people better for that sort of compromise opportunity if there is. I think we have one more question.
I was just wondering, in today's political climate, how do you think about building policy that can resist changes in partisan politics between different terms?
We've already failed.
Yeah, I don't.
Look, one thing I will say is, policy goes up and down, and we're going to make sure we have representation across the political spectrum. Come talk to this class, because we think that's a really valuable asset for students to understand how people on both sides of the spectrum are actually thinking. Part of it is, scientists inspire new possibility, new sense of possibility. So, you can get dejected by what's the sort of discussion, but I'll tell you that there were probably a lot of moments in the 8 years in the Obama administration where I felt like we were the naysayers. We were the people who said, well, this is not possible. And we had people, some Stanford folks, Arun Majumdar, who heads up, along with Sally, heads up pre-court, at that time was running ARPA-E, and he said, no, there is possibility if we take the risk. Mm-hmm. So I think one piece of it is, as scientists, you have an opportunity to explode the status quo of what people think is possible. And then the second is, you guys all operate in a world of experiments, and things go bad all the time, and you move on, you keep trying. And I think part of what we want to do is help you understand the policy domain also has gears. It also has, some rhyme and reason, and part of it is things break down, and then you tune up and you keep going. But we want to help you sort of get some pattern recognition for how those gears work.
Yeah, and I think one thing that's been true as long as I've been involved in research is that there has been pretty consistent bipartisan support for basic research in this country, and also for the production. Probably our greatest product of this is you. We're producing great, educated PhDs and master's students who can go out and have an impact on the world. I think that those things are pretty generally supported, across the board.
The last thing I'll just close with is, I know folks have talked here about sort of the softer side of policy, what I think of as norms and sort of social mores. We enter through the lens of sort of U.S. federal policy around research, but I really think what our goal is to help you understand how the system around sort of mores, social norms, soft law and hard law operate in this space, and the role that technologists and scientists can play in that. Thanks.
Thank you.